So last class we had started talking about re-expression, and we talked about the different ways that it can help histograms and box plots through becoming more symmetric and nearly normal and being able to make spreads more comparable. But today we're going to talk more about scatter plots, which is what we're really talking about in this whole section, and how re-expression can help them. So linear scatter plots with evenly spread scatter are easier to model, as we've seen. So once we straighten a scatter plot, we can fit a linear model to it, which is the goal here. Okay, so if you take a look at this scatter plot here, we just have regular assets, and it looks a little curved. It also looks like we've got a lot of points close together here, and then they spread out over here. So in that case, a couple of conditions aren't going to pass. What we've done here is re-express using a log on the y value, and now take a look at that scatter plot. A lot more straight looking, no thickening on either end, and a linear model would fit a lot better. Okay, so this is what re-expression can really do to help us to be able to pass those conditions and create a linear model. So how do you know which re-expression to use? Well, here's a table with a lot of good information. I'll run through it with you. But this is called the ladder of powers. And basically you're going to start at the raw data part, and you're going to go through either up the ladder or down the ladder, trying different re-expressions until you find one where your scatter plot looks straight enough. All right? And your residual plot looks good too. So let's go up. This is just your regular y values. If you have data with positives and negative values and you don't have bounds on either end, re-expression really isn't going to help, and you're kind of stuck. Otherwise, we can try the different parts of the ladder of powers to be able to try to re-express and make the data look more straight in the scatter plot. Okay, so if we went up the ladder, we would use squaring the y values. Okay, and this is good if one of your variables is unimodal and skewed left. It can really help you out. Okay, if that doesn't work, you could keep going up and do a cubing the y's, going to the fourth power, etc. Otherwise, you move down the ladder. And the one down below it is square root of the y's. Okay? This is good when your data is in counts, so it can be really helpful for that. If the square root doesn't really work out for you, you can go to logarithms, right? And usually we take log of y, or we can actually take the natural log, ln of y. But for you to be able to use logs, you can only have positive values, because you can't take a log of a negative. Okay, so that's the kind of limitation you have there. Next down the ladder is the reciprocal square root, so that would be 1 over the square root of y. And if you're putting y in the denominator, if your direction was positive, then larger y values would actually make that reciprocal smaller. So what you have to do to fix that is change the sign. So that will keep the direction of your relationship so it's correct and the same as it was before. Because if you're talking about a scatter plot and you see a positive direction and then you re-express and now it's negative, that's just kind of confusing to interpret. Okay, so we want to keep the direction the same. If the reciprocal square root doesn't work for you, you can just do a regular reciprocal, so 1 over y, but again, you got to change the sign. If you have any values that are 0, obviously you can't divide by 0, so you'd have to add a small constant to all of your values. The reciprocal is good for ratios specifically because remember we talked about miles per hour versus hours per mile. So if you're kind of choosing what that ratio for your units is, then sometimes the reciprocal is actually better. Right? So those are the options you have. Like I said, you start with the raw data. You can move up or down. If you try one and it doesn't work, just keep moving. Okay, so you look at the scatter plot, you look at the residual plot, and either it looks good or you're like, I should probably try something else. And if you go too far and you're like, well, that really didn't change anything, you can always go back to the step before, and it's no big deal. All right, so what we're going to do next is talk about trying to figure out what step in the ladder is most useful to start at. Because if you can make a good educated guess for a start, then it's less work for you to move up or down, and you don't have to go through every single option. So you want to model the relationship between number of birds counted at a nesting site and the temperature. So those are your variables. Number of birds counted and temperature in Celsius. The scatter plot of counts versus temperatures shows an upwardly curving pattern with more birds spotted at higher temperatures. So notice it says upwardly curving pattern. So that means a re-expression is going to be necessary, right? Or we're going to try one at least. So what transformations, if any, of the bird counts might you start with? Well, what do you notice here? It's in counts. And we said for data in counts, we would use square root. So that would be a good starting point for this one, because it's in counts. Okay. You want to model the relationship between prices for various items in Paris and Hong Kong. The scatter plot of Hong Kong prices versus Parisian prices shows a generally straight pattern with a small amount of scattering. If it says it's generally straight, should we really re-express? No, it's already straight enough. Okay, so don't waste your time going through re-expressions if it's already straight. There's no reason for that. All right, and the last example. You want to model the population growth of the United States over the past 200 years. The scatter plot shows a strongly upwardly curved pattern. What transformation, if any, of the population might you start with? So, population, that's counting people. So maybe you're thinking square root's a good option. But let's think about the values of population. Aren't those really big numbers? Millions, billions? There's a lot of zeros on there. When you're thinking my values have lots of zeros, we're going to go with logs. Okay, so I'm going to go logarithms because the numbers are big. So this might be better than square roots. Of course, if it's not, you can always go back. Okay, again, those are just starting points. You can go through the whole ladder if you really want to. There's nothing wrong with that. Let's talk about an example where we're going to go look through some scatter plots and see how re-expression kind of impacts them. So it says monofilament fishing line comes in a range of strengths, usually expressed as test pounds. 5 test pound line, 5 pound test line, for example, can be expected to withstand a pull of up to 5 pounds without breaking. The convention in selling fishing line is that the price of a spool doesn't vary with strength. Instead, the length of the line on the spool varies. Higher test pound line is thicker though, so spools of fishing line hold about the same amount of material. How are length on the spool and strength related? What relationship or what re-expression will straighten the relationship? Okay? So if we're talking about the relationship between two variables, we're probably thinking about creating a linear model if they're quantitative variables. And so we want to check conditions to be able to do that. Do we have 2 quantitative variables? Yeah, we do. Right? We have length in yards and we have strength in pounds. So this condition passes. Okay. Is it straight enough? Do we have any outliers? Does the plot thicken? We'd have to look at a scatter plot to be able to determine those. So here's a scatter plot of strength in pounds versus length in yards. And what do you think? It does not look straight enough. There don't seem to be any outliers. And I can't check does the plot thicken because I don't have a residual plot. But it looks curved, so I'm going to have to try a re-expression. Okay, so this has a curved form. We can see that the relationship is negative in direction. It's pretty strong, right? Look at how they fall into that curve, right? If you think this is your relationship, they all pretty much fall in line. And like we said, no real outliers here. We can't use a linear model as it is. Okay, so that means Now that we know about re-expression, we would try to re-express. So here we're using square root of length, which you can see on the y-axis, they filled in there. Okay, how does it look? It looks mildly better, but is it straight? No. So what does that mean? Keep moving down the ladder. On the next page, here's a re-expression using logs, which you can see by looking at the y-axis. This one, again, is better, but still not straight. So we keep going. Yeah, this is a lot of work, right? If you've got your own data and you're trying to figure this out, it's going to take some effort, and that's okay. Sometimes you'll get lucky and it'll be one of the first ones you try. Next, we're doing -1 over the length. So this is a reciprocal. Looks good, right? But I got a little too excited and I skipped a step on the ladder. Let's go back and see what that would look like. Here is the negative reciprocal square root. Now, you might be thinking, this one doesn't look as straight as the one before, but it still looks good, okay? We're not trying to be perfect here. We're just trying to get it straight enough that we can fit a linear model and we didn't break any crazy conditions. So if you can move down the ladder less, that's actually better. So I'm going to stick with this one. Once you pick a re-expression you like, you've got to recheck your conditions. Obviously, if we had quantitative variables to start, they're going to stay quantitative variables. So you don't need to change that. You don't have to recheck it. But is this straight enough now? Yes. All right, look at that scatter plot. It looks good. And then also, we need no outliers. That also passes. Of course, if you're doing this on your own, I would want to see you write out the condition name and then a little sentence next to it. For now, I'm just putting this here so you can see that we rechecked them. Okay, but I'd want to see all that work. Now that we have picked a re-expression, we need to model it with an equation. And I have the numbers for you. So we have A is -0.023 and B is -0.000373. So we're going to take that and we're going to plug into our y hat equals A plus bx so that we have an equation here. Okay. Our y variable is length. But remember, we chose this one here, which used -1 over the square root of length. So that's what you have to put instead of y. -1 over the square root of length hat, because that's what you're predicting. Don't forget the hat. So if you're someone who types your homework, you might be thinking chapter 9, that's probably not a good idea. A is -0.023, B is -0.000373 times x, which is strength. And that's what your linear model looks like. So it's super important that you have this part here. If you don't have this part, then whoever looks at your equation isn't going to know what re-expression you did, and they're not going to know how to use your equation or interpret it. So you got to have that in there. Okay. But now that we have the equation, we can use it to predict values of the length given the strength. So here we're told to predict the length of a spool that has a 35-pound test line. Okay. So let's see. I'm going to take my equation down here. I'm just going to make it smaller. And I'm going to plug in 35 for the strength. If if I simplify the right-hand side, I get negative 0.036. Okay? And if I stopped here, the units, I'll write them down for you, are going to be negative 1 over the square root of yards. So you walk into the store and you say, I need to buy negative 0.036, negative 1 over the square root of yards of lime. And they say, what are you, crazy? Right? That doesn't make any sense. So we really want to find length hat. So we're going to have to do some maneuvering here. All right? So I don't really want these units. I want it to just be in yards so I can talk like a normal human being. So length is in the bottom of our fraction. We got to get it out. So I could multiply both sides by the square root of length and then divide by this number here. Or I can just do a little flip-flop. You might have seen this in some algebra classes before that you can do this. And I'll end up with negative 1 over negative 0.036 equals the square root of length hat. Now, how do I undo a square root? I square both sides. And that'll get me length hat. If you put it in the calculator, 771.6. And now we're in yards because it's just regular length. And then, of course, you would say something like, according to the model, if I had a 35-pound test line, I would predict that the length would be around 771.6 yards. All right, I'm not going to write that sentence here, but you can write it yourself if you want it. Okay, so the important thing here is that you're including that re-expression in your equation, and then you know how to undo the re-expression to get back to the y hat. Okay. Next, when your curve is really strong and none of the data values are 0 or negative, you can use logs. All right, and this first part, so we got plan B, attack of the logs. This is for when you go through all the steps in the ladder of powers and you're like, none of them really worked. I need something better. So you go to plan B. And plan B starts out with actually the 0 power from the ladder. Okay, we call it exponential. And that's when you take the log of your y values. And this can be regular logs or natural logs. So log base 10 or natural logs are fine here. It doesn't really matter. But this one is good for your values if they grow by a percentage or if you kind of see that happening like an exponential function. Okay. Next option is logarithmic. That's when instead of taking the log of the y's, you take the log of the x's. And this is good for when you have a wide range of x values or a scatter plot that descends quickly on the left and then evens out. So think about what a logarithmic function looks like. Looks kind of like this. If your data kind of looks like that, then logarithmic option is the way to go. Remember, exponential kind of looks like this. So if your data looks like that, that might be the way to go. If neither of those work, we go to the Goldilocks model, which is your power model, and that's when you actually take the log of both x and y. Okay, so that's your last resort. You tried everything else. You're like, I just can't do it. You take log of both and hope for the best. If that doesn't work, you're done. All right, I got this warning down here. Don't expect to be able to straighten every curved scatter plot. Okay, you try out some of them. You go through. You're like, it's just not getting better. You look at the residual plots and they don't look better. That's okay. You tried. You say, here are some examples. Here are my scatter plots. You can see they don't look good. I got nothing left. Okay, you can't fix everything. Something else you might be thinking, if there's a curve in the scatter plot, why don't I just fit a curve to the data? Well, it turns out that the math behind curves of best fit is very complicated. Too complicated for us to deal with in this class, and also harder to interpret, right? If you've got some sort of quadratic function you're trying to talk about, those numbers in front of the variables, they don't really mean a lot to an everyday person. But if you have a straight line, it's easy for everyone to understand, and you can easily interpret your slope and your y-intercept, right? Y-intercept, starting point. Everyone understands that. Slope, as this goes up by this much. Easy things for you to understand and for the people you're trying to explain your model to understand. Okay? So we're going to stay away from curves. We're just dealing with lines in this class, but I just wanted you to know where I'm coming from there. Okay? You might have noticed when you're using linear regression in your calculator that there are these lovely functions called quadreg, cubic reg, expareg, where it seems like you take curvy data and you use this and it magically gives you an equation. Well, turns out the people that made your calculator aren't really statisticians, and these aren't the best functions to use. I put them in quotes, functions in quotes, because they're really not good, okay? So, as tempting as it might be to say, well, I don't want to go through the ladder of powers, why don't I just use one of these? Don't use them. They don't count for anything in this class. They don't count for anything on the AP exam. They aren't even really that great. Don't do it. Okay? LinReg, that's the one you use. That's the only one you use. Re-express your data. That's why we have a whole chapter about it. I wouldn't teach you all that stuff and then say, hey, go press this one button and you don't have to deal with it. Right? That doesn't make sense. All right. Those are the basics of re-expression. Now, we talked about logs, and I said don't be scared. I'll teach you about everything you need to know. Well, let's do some log review, okay? Really, the only thing you need to know, besides how to press the log button on your calculator, is how to undo a log. You don't need to know log rules at all, just how to undo a log and how to press it on the calculator. That's it, I promise. So, say I have this equation, and I just use some easy numbers to make my life easier and yours. So I got log y hat equals 2 plus 3x, and I'm going to plug in x equals 1. Okay? So say I'm trying to predict where x is 1. I plug that in. So I get log of y hat equals 5. And now, I don't want to know about log of y hat. I just want y hat. So I need to undo that log. Now, the opposite of log, the common log, is 10 to the power of. So we're going to exponentiate, where you take the base of 10 and you make that the base of your exponent on both sides. What that does is cancel out the log, so you're just left with y hat. So y hat will be equal to 10 to the 5th, or 1 with 5 zeros. Okay? Obviously, you're not going to be dealing with numbers as clean as 5. You're going to have decimals in there. But your calculator can tell you 10 to the whatever power, and you can go from there nice and easy. The cool thing is that right above the log button on your calculator is the 10 to the power of button. So in case you forget, you just look at your calculator and it says, hey, we undo each other right there. Okay? Say you have a function like this, where you took the log of the x's instead of the y's. Well, for this one, all you got to do is plug in, and then this is going to be equal to a number. You don't have to undo the log. You're just going to get a number in there. You type the whole thing in your calculator, get a value. That's it. Okay, so that one's nice and simple. If you got logs on both, then you'll get a number here, and then you got to do the 10 to the power of whatever to get rid of that. The last thing we need to talk about is if you had natural log. So if you have natural log, do you know how to undo that? That's the question. What's the opposite of the natural log? E. E is the opposite. So E is a number that's like 2.71 something. Just a number. Oops, I should have simplified this first. ln y hat equals 5. Sorry. So you do e to the stuff. So these cancel out. You get y hat equals e to the 5th. You put that in your calculator, and you get a number. Okay?